Good afternoon, everybody. Today I'm going to talk about subvector machine. Subvector machine is actually one of the most important and successful machine learning algorithm, which led the boom of machine learning around 2000, just before deep learning came out. Compared to deep learning, subvector machine is really much more practical and works well for small data regime and have strong mathematical or learning theoretical ground. Since initially I want to go deep into the Lagrange multiplier and convex optimization, which is central part of subvector machine, but then I decided to focus more on bigger picture. So I'll try to go to the final form of subvector machine that people use nowadays very often. So I prepared Lagrange multiplier part, but I'll cover it only if I have some time left. So see if I can do it or not. I think many of you are also familiar with subvector machine. How many of you are not familiar with subvector machine? Yeah, I hope I provide some new information for you guys. Let's first talk about the classification problem in machine learning. Classification problem is separating data points in the vector space, feature space, into their original category. Then there are two major approaches in machine learning to solve classification problems. One is to learn. I think Jisoo have covered it last seminar. We first learned the probability density of each class or each category, and then do classification based on their probabilities, P1 or P2. We compare the probability and do classification. The other approach is ignore probability, then just learn the decision boundary between the two classes. The first one is called generative approach, and the second one is called discriminative approach. The two approaches are the central two pillars of machine learning, and they have really distinct characteristics and interesting relationships, but I won't cover it in detail today. But at least you have to know the word, the term, and the concept. Well, I guess last time Jisoo have covered the generative approach. I'm gonna cover the discriminative part today. Well, yes. So, among the discriminative approach of discriminative methods, the most simple one would be binary linear classifiers, which means we just simply learn linear boundaries between the samples, and we are only considering we are assuming that there are only two categories of data there. This is binary linear classifier or binary linear classification. This is the most simple classification that we can have, and therefore therefore, we can approach it with some theory. Because if the decision boundary is so complex, then we cannot treat it with rigorous mathematics. But if decision boundary is similar and problem is similar, then it is tractable. At least we can try to understand what is going on beyond this kind of classification. Well, the most well-known example of this kind of boundary can be deep learning. But SVM, which I will talk today, is based on binary linear classification. Any questions so far? So let's first, let's try to come up with some examples of binary linear classifiers. The most famous one may be Perceptron. I think most of you have heard of these words. Perceptrons are really binary linear classifier itself. It does inference by this kind of equation, which means you have input vector x, and so model has weight vector w and the bias scalar b, and model do inference by doing inner product between the weight vector and the input vector and apply threshold and see if it is plus or minus. The sign means to check. Sign will output +1 if this is positive. It will output minus if this is negative. So Perceptron does such kind of inference, and the other one may be logistic regression, which is logistic regression, and vicious linear discriminative analysis. Such examples are all linear classifiers which are aiming to find linear boundary between separating classes. Well, yeah. 한국말로 해주세요.
로지스틱 리그레이션 지금 9시 0에서 1까지 나올 수 있는
예, 좋은 질문인데요. 네, 사실 이렇게 동등하게 녹화. That was a good question. So my formulation was ill. So I will try to. Logistic regression can be interpreted as a probabilistic measure. So it outputs between 0 and 1, and it can be interpreted as a probability of being a class 1. So
퍼셉트론은
it's not probabilistic.
그러니까 1 아니면 -1이 나오는 거고, 두 번째 거는 확률은 0에서 1 사이에 나오는 거죠.
That was a good question. So these are linear classifiers. So there are obvious limitations of those classifiers. They are namely, they're binary, they're linear. Those things are obvious drawback, obvious limitations. So it is not really practically applicable, practically useful. So, but then one more thing I want to come up is model selection problem. I will talk about this over. So let's say if you are learning a Perceptron, so there is sample +1 and sample -1, and you learn some kind of separating boundary. But in fact, there are many possible separating boundaries. For example, this one, and that one. In most of other algorithms, for example, Perceptron. Let's just stick with Perceptron. In Perceptron, there is no criterion to select between these kind of possible boundaries. Okay. Well, in logistic regression, you can do something with other kind of criterion, but generally speaking, there is no fine, really sound criterion for selecting boundaries between those kind of candidates. Well, maximum margin classifier, which is this is basically another name of support vector machine, provides criterion to select among these boundaries, which is maximum margin. Support vector machine or maximum margin classifier tends to find the boundary which has maximum margin, which means so maximum margin classifier tends to find the boundary which has the maximum gap to the first example it faces in each classes. Does it make sense? 무슨 말인지 아시겠죠? 네. 그 maximum margin이라는 게 margin이라는 말이 이 separating boundary에서 여기 처음 example이 있는 곳까지의 거리, 요 중간지대 영역의 넓이를 최대화한다는 뜻이에요. Yes. So in this figure, the length of this line or this line is called margin. It is important to note that changing margin actually, let's just see examples. To simplify the problem, let's say we have only two examples, one for each classes, and compare with max margin classifier between from which is none, from what is none. So in this example, maximum margin classifier should look like this, and this would be margin. A classifier which is not a maximum margin classifier will look like this, and the margin will be here. You see the difference? Even though they are separating between the two classes perfectly, like 100%, they can have different margin, and also a different margin means different shape. Well, I hope this makes sense to you. Then the immediate question should be, why maximum margin? Why should we look for maximum margin? Well, you should raise this question. And there is, as far as I know, there is only approximate answers. These are heuristics. Well, there are good justification from statistical learning theory or current density estimation and things like that, and all the big guys out in machine learning try to answer this question. And there's also explanation regarding VC generalization bound, which you guys might have learned last time. But all of them are, I don't think all the explanations are 100% valid, but then these can be just considered as a good heuristic in classification problem. At least it works awesomely well in practice, so people are stick with this. There can be better classifier than maximum margin classifier. Any questions regarding maximum margin? 네.
레이블 A가 되는 게 이렇게 있고 B가 되는 게 이렇게 있어서 삼각기가 애매한 경우는 저런 게 있죠.
삼각기가 애매하다는 게 저렇게 리니어 바운드를 찾을 수 없는 경우 말씀하시는 거죠?
아, 그러면 그 경우는
그럼 그냥 아예 해가 없는 거예요?
해가 없기 때문에 이런 논리가 상관이
그럼 그게 아예 여기 해당이 안 되는 사이.
그 O하고 X가 딱 하나로 정하기 하나로 정할 수 없을 경우도 있잖아요.
하나로 정할 수 없다는 거.
그러니까 OX를 어떤 걸로 잡느냐에 따라 선이 D가 달라질 수 있잖아요.
피처 스페이스가 바뀐다는 거.
그러니까 여러 가지 O가 있고 여러 가지 X가 있는데 특정 O를 잡고 특정 X를 잡은 다음에 이제 그 사이의 거리를 그 사이의 거리를
이제 이것처럼 O가 여러 개 있고 X가 여러 개 있을 때 어떤 O까지 거리를 최소화하느냐는 문제를 말씀하시는 거죠. 그 사실 제가 연습 문제를 좀 만들어 보려고 했는데 일단 마진의 정의가 제일 가까운 것까지의 거리이고 그런 조건을 요거를 최대화하도록 잡으면은 데이터가 한 번 주어졌을 때 거기에 해당되는 게 한 가지밖에 없어요.
기울기를 일단 정해가지고 저 2차원이라고
아니요, 이 기울기를 만약에 다르게 긋게 되면은 마진의 크기가 바뀐다는 거예요. 그러니까 이 마진을 최대화하는 그 기울기가 하나밖에 없어요. 그 마진을 최대화하면서 둘을 분리하는 그 바운더리가 한 개밖에 없어요. 왜냐면은 이 경우에 그래서 이걸 보여드린 건데 O랑 X가 이렇게 있으면은 이거 말고 그러면은 다른 거를 그으면 어떨까 해서 얘를 중심을 그대로인 채로 그냥 이렇게 옆으로만 기울였다고 해도 마진이 바뀐다니까. 그래서 마진의 정의가 여기까지 수선의 길이 있는데 그렇습니다. 근데 그래서 실제로 데이터를 이렇게 그려놓고 바운더리를 찾으려고 맥시멈 마진 바운더리를 찾으려고 하면은 의외로 사실 생각보다 그러니까 좀 헷갈려요. 이게 맥시멈 마진이고 이게 맥시멈 마진이고. 근데 이제 하다 보면은 그걸 최대화하는 건 한 개밖에 없어요.
그러면 이제 저렇게 하나로 딱 주어질 수 있다는 보장을 할 수 있는 환경이 성식하거든요.
네, 그거에 대해서 좀 얘기를 해볼까요? 그 얘기를 하기 전에 one of my intention to preparing this lecture is to give a basic idea of optimization, mathematical optimization. So I'd like to provide some introduction to optimization problems. So, the reason why I'm talking about optimization is this problem can be formulated into a mathematical optimization problem because, for example, in other words, this is a this can be viewed as a constraint optimization problem, which is to minimize maximize the margin subject to the constraints that all the training examples should be classified correctly. So I will talk about that later. So let me first review some introductory concepts of optimization. Well, most of these materials come from the really heavy but good book of Convex Optimization. Which is written by the famous Professor Boyd, who is in Stanford. There is a class named 최적화 기법 in 전기과, which is given by 최진영 교수님. 최진영 교수님이 하신 최적화 기법. There is a class named 최적화 기법, and that class mainly deals with the convex optimization techniques, and the class is a little bit demanding, but it is worth taking because it gives the basic introduction and very sound training of optimization. Anyway, the canonical form of optimization can be written like this. This is the canonical formulation of general optimization. So we want to minimize or maximize. It is really easy to convert minimization problem to maximization problem. So we are just stick with minimization. We want to minimize some objective function or target function f0. But if we only have this, the problem is called unconstrained optimization. But in reality, or many other practical problems, there are constraints, and there are two kinds of constraints, which are inequality constraint and equality constraints. So in general, this form shows the general scheme of constraint optimization. Well, there are some other terms to introduce. The set of X which satisfies those constraints is called the feasible set. The feasible set. And the optimum is defined. I don't know why they use infimum, but I don't want to raise a question to Professor Boyd. So among the all possible value of objective function, we find the smallest one, and that's the optimal solution for this problem. If there exists, this is the problem. This is a basic formalization of optimization problem, and you should be familiar with this kind of question against this because this is definition. Well, among this kind of general optimization problems, there are special kinds of optimization, which is called convex optimization. Convex optimization, the specification of convex optimization is quite simple. First, the objective function fx should be convex function, should be a convex function. And the second constraint is the physical set, the domain, should be also a convex set. Well, these are why this optimization is called convex optimization. But even though the word convex, they share word convex, the exact meaning is slightly different. And let me introduce the definition of each term. If a function is convex, then the function satisfies this kind of relationship. If function satisfies this kind of relationship for all x and y in their domain, the function is called convex, which is the basic example can be drawn as y equals x squared. This means if you pick x and y, actually this is really bad. If you pick x and y and you draw a line between them, the lambda x plus 1 minus lambda y should lie between x and y, somewhere here. And its function value is always lower than the weighted average of each function value. 혹시 이 영어 설명하실 때 무슨 말인지 다 알아보시겠어요? 이게 컨벡션 아래로 볼록인 함수의 정의죠. If a set is convex, like slightly similar but not exactly the same constraint should hold for every x, y in the domain set, the physical set. This is a definition of a set to be convex. Yeah, you see the recurring form of this kind of equation. This is called convex combination. And here, of course, lambda should lie between 0 and 1. This is called convex combination because this value cannot go outside of x or y, neither x or y. These are definition of convex optimization. Any questions? Why I am introducing convex optimization is because convex optimization has really good properties. convex optimization. Because, first of all, it has really awesome property that local optimum of convex optimization problem is always same as global optimum. You may, if you are familiar with neural networks, you're probably familiar with the concept of local optimum in the process of optimization process. Well, neural networks, they argue about whether local optimum is close to global optimum or not. But in convex optimization, it's mathematically proved that local optimum, the problem attained at the solution attained by local optimization technique is always same as global optimization. A global optimum. This is the first benefit. The second one is the solver is very efficient. It's not efficient solvers. There are since convex optimization has a very general form, there have been many good efficient solvers. I mean, if you wanna solve a convex optimization problem, you really don't have to worry about solvers. There are many good solvers out there. And this may be the answer to your solution, because finding the problem of finding maximum margin can be formulated into convex optimization problem. In convex optimization, the local optimum is always same as the global optimum. So in that problem solution, stand for each boundary or found the decision hyperplane is always same as the best separating hyperplane. 그러니까 무슨 말이냐면은 그 컨벡스 옵티미제이션이기 때문에 항상 최적의 바운더리를 찾으면은 그게 진짜 내가 찾고 싶었던 거랑 거의 항상 이제 그거와 아주 같다는 거죠.
질문이
네. 해주세요.
컨벡스 펑션이라고 해도
네.
만약에 데이터 D를 가정하게 되면은 뭐 데이터 1번부터 n번까지의 합으로 이렇게 표현을 하게 되는데 오브젝트 펑션이 그렇게 되면 컨벡스 펑션의 합은 컨벡스가 아니게 되는데 그렇지 않아요?
컨벡스 펑션의 합은
컨벡스 펑션의 합이 컨벡스가 안 될 수도 있지 않아요?
없습니다.
예를 들어서 2차 포물선이
네,
있는데
어쨌든 말씀하시는 의도는 어쨌든 최종적으로 오브젝티브 펑션이 컨벡스가 아닌 경우에는 쓸 수 없지 않냐라고 하는데 하는 말씀이신 거죠. 어쨌든 제가 무슨 프로세스를 거쳐서 최종적으로 컨벡스 펑션이 아닌 게 나오면 그런 거는 아니에요. 그러니까 그런 거는 여기에 들어갈 수 없어요. 다른가요? 그러니까는 중간 프로세스 무슨 라이클리우드가 컨벡스이고 이런 게 중요한 게 아니라 최종적으로 내가 옵티마이즈하는 펑션이 컨벡스여야지 여기에 해당이 되는 거죠. 그러니까 만약에 형님 말씀하신 대로 중간에 무슨 계산 합이든 뭐든 통해서 컨벡스가 아니게 됐으면 여기에 있는 걸 적용할 수 있죠. Then let's build maximum margin search file. Let's say we have some two-class data, and we label each class class -1 and +1 for mathematical simplicity. And we want to find maximum margin decision hyperplane like this. And in this case, margin should be the distance of this dotted line to the separating hyperplane. This is margin. And since this is linear function, the functional form should be given by W transpose X minus B. In fact, we want our classifier to classify future examples by this kind of classification rules. With our learned weight vector W and the learned bias term B, decided by finding this classification boundary, we want to do classification exactly same as how Perceptron does. This is our design of the model. Then, anyway, how to find such W and B is different. What is different from Perceptron? And if you draw weight vector in this diagram, weight vector should look like this. Since in order to do inner product between W and X and W and X should be in the same dimension, so it can be drawn in this figure. And this should be perpendicular to the decision boundary, as your vector calculus says. You should note that here we can choose. We are free to vary its size, its norm, because this and this weight vector should yield the same decision boundary. Agree? If we adjust B properly. 그러니까는 여기서 W로 마음대로 바꿀 수가 있죠. 왜냐하면 W는 방향을 나타내는 데 쓰는 거니까 결국에 크기를 어느 정도로 잡든지 간에 이게 흔들리진 않는 거잖아요. So by exploiting such freedom, we do a little trick so that for examples in this dotted line, this formula should always produce +1. And for examples in this dotted line, examples should +(-1). We can make it by scaling W. Agree? This constraint doesn't hurt the big picture. This is our constraint. Okay. Then let's see. Well, D is even though D is our objective, D is not. We don't know how D is represented, so we need to calculate D in terms of our other variables, W, X, and B, such things. Well, in order to do that, I'd like to use your imagination to project all data and hyperplane into this line, which is proportional to W. Then it should be look like this. All these data the data on the border should lie here. Agreed? This 3 should project it here, and the other will lie somewhere behind. And these should lie here, but I'd like to put another axis. yi means the label of the data. So all of these data are -1. All these, all yi's of these data are +1. So in order to draw properly, the data should project it like this. And this value must be -1, this value must be +1. Is it okay? 말이 되나요? 그러니까 이 DC랑 하이퍼플레인의 그 방향 벡터 W 방향으로 모든 것들을 다 프로젝션해서 생각을 해보자는 거예요. 좀 생각하기가 쉽게. Then our decision hyperplane must look like this. This is our decision hyperplane. 말이 되게 되는 얘기를 하고 있는지 모르겠는데. In this case, where we can find D? If as we define D like this, the distance from this dotted line to this dotted line should be 2D. 2D should be find here. This is 2D. And to go one step further, in this two-dimensional figure, if we calculate the slope of this line, that would be norm of W vector. 제 생각에는 소프트웨어 모션에서 이게 제일 헷갈리는 것 같은데 혹시 여기서 질문이나 뭔가 이해가 안 되는 거 있으신가요?
X축이
여기 X축이요.
거리를
거리죠. 예. 그러니까는 이게 데이터가 2차원 공간에 살고 있었는데 2차원으로 생각하는데도 지금 y까지 생각하려면 3차원이 되니까 너무 힘드니까 어차피 지금 이 디시전 하이퍼플레인 기준을 생각할 거니까 W 벡터 방향으로 어떤 뭐 여기 기준선이 있다고 해가지고 전부 사형, 그 정사형을 시켰다고 생각을 하는 거예요. 그러면은 이 더티드 라인은 항상 얘랑 평행한데 그럼 여기 있는 녀석들이 다 프로젝션 되면 여기 다 겹치겠죠. 여기 한 칸으로. 여기 쭉 다 겹치고. 근데 이렇게 쭉 다 겹쳐서 그린 다음에 각각의 y 값에 대해서 이렇게 표시를 해주면은 여기서 여기에 이제 있던 높이를 옆으로 볼 수가 있는 거죠. 내 생각에는 이걸 네. 저도 한 번에 알았던 건 아니니까요. Our current what we are doing is to find margin's expression in terms of other variables. Since we don't have D in our model, so we want to express D in terms of other variables. In order to do that, we do some geometrical inspection. So if we are basically looking from this side, which is this kind of picture, and so the margin we want to find is here. So we can do a trick with this one. Well, the definition of slope is x increment. So we can just inspect this triangle. X increment is the twice of margin, so 2D. A y increment is -1 to +1, therefore 2. So it's 1 over margin. So in conclusion, margin can be expressed in terms of the norm of W, then that is 1 over norm of W. This is the size of margin.
네, 저기 W값이 커지면
예.
그러니까 W가 방향이 같으면 저 기울기는 같은데 저기서 사실 그러니까 W 벡터가 방향하고 크기만 다르다 됐을 때
네.
마진이 변하지 않는 것 같아요.
방향이 같고 크기가 다르겠어요. 말씀하신
네.
W.
네. 아니면 저 W 행렬의 노름값이 커지면 반드시 다른 위치에 가게 되죠.
일단 그런 건데요. 아까 그 보여드린 예시랑 같이 방금 거에 대해서 설명을 하면 말씀하신 내용을 이걸 정해주면서 그 자유도가 없어졌어요. 맨 처음에는 제가 W 크기 바뀌어도 이게 똑같지 않냐고 했잖아요. 지금 그 자유도를 여기 있는 것들을 Y값을 -1이랑 +1로 바꿔주는 거에다 썼어요. 무슨 얘기냐면은 여기서 이걸로 생각하면 조금 편한데 여기서 방금 말씀하신 것처럼 방향이 W 방향이 그대로 크게 커지는 거는 이거의 기울기를 올려주는 건데 이거의 기울기를 올려주게 되면 B를 어떻게 움직여도 이걸 맞출 수 없어요. 맞죠? 맞죠? 그러니까는 이제 처음에 얘기했던 그 W를 마음대로 바꿔도 된다는 자유도를 여기에서 정해주면서 써버렸어요. Final optimization formulation of maximum margin classifier can be also just for that. So our initial objective was maximize D, but we then figure out that D is the inverse of norm of W. Then we can, so maximize D means maximize 1 over W, but 1 over W, we hate those kind of functional maximizing 1 over W is exactly the same as minimizing W. However, well, you all know the norm of W is defined as W transpose the root, square root of W transpose W. So square root, I don't like that. So we can modify it further. This wouldn't change the solution. However, it eases the optimization process. Well, for further mathematical convenience, we can just put 1 over 2 in front of this. So this is our objective function. Minimize the square norm of W. However, our constraint is to classify all the training examples correctly. So subject to xi is in class 1, this should be bigger than +1 because y is increasing that way. Actually, f is this line is increasing that way, so it should be bigger than 1, and vice versa. So this is mathematical learning formulation for maximum margin classifier. And this exactly follows the form just I presented before, the mathematical form, general mathematical framework. Well, to inspect a little bit, our free variable is W and B. This function is quadratic function. This is a quadratic of W, which is known to be convex function. And about this kind of constraints, inequality constraints, these are called this kind of these are linear constraints that can be also people also call those kind of things affine forms, which are also convex. So in this case, the objective function is convex and the constraints are affine, therefore convex. So making all the process as a convex optimization, which is very efficiently solvable. This is the core of maximum margin classifier. So it achieves 여기까지 질문이 있네요. 여기서 더 할 얘기는 없는데.
저기 네. XI랑 XG가
트레이닝 example.
네, 근데 같은 집합에 속하네.
마이너스 1 클래스 마이너스 1. Well, actually this is not the whole story. There are a bunch of interesting stories beyond, because this kind of original formulation of convex optimization problem is called primal problem. Well, it is known that from mathematics, optimization theories, primal problems can be converted into dual problems with some interesting techniques. And dual problem has many more many more advantage over solving primal problems sometimes. Well then, the solution of primal problem, let's say that's P star, and solution of dual problem is not necessarily the same in general. However, in convex optimization problem, these two are exactly the same. So, in reality, what LibSVM does is basically convert this problem into dual problem, which I won't probably address today, into dual problem and solve the dual problem to get the answer of primal problem. It is really interesting to see what's going on in that process. I will not probably talk about that today. Just go to 듀얼 프로그램에 대해서 얘기를 한 게 커널을 얘기하기 위해서 좀 해야 될 수도 있는데 뭐 일단 되는 거 해봅시다. Before we proceed, let's just talk about the benefits of maximum margin classifier or support vector machine. There are several benefits over other kind of machine learning. Well, first, the learning process is formulated as a convex optimization, which has very efficient solvers. So learning is fast and very efficient compared to other kind of, for example, stochastic gradient descent in deep learning. It's really, really fast. I think nowadays it can really you can run the solver in really poor performing CPUs, for example, your cell phone or your Nintendo 3DS and things like that. And the other thing is that in order to and first, learning is fast. The other is it generalizes well. In other words, it has lower test error because selecting maximum margin has some learning theoretical background. For example, minimizing the VC confidence bound, it tends to perform well compared to other kinds of linear classifiers. And the third one is I have to say this I should have explained the dual problem in order to say this again. In the process of solving this optimization problem, we should introduce something called Lagrange multiplier, which and because of that, let's say, so this is our final model. We only get to know W and B. Then, to calculate W, we only need examples on the margin boundary because of some mathematical elegance. So, 무슨 말인지 아시겠어요? 그러니까는 예를 K nearest neighbor라든지 some machine learning algorithm, for example, especially non-parametric methods, for example, K nearest neighbor or Gaussian process, they need to keep all the training data to do the inference. However, in support vector machine, the solution for W is only dependent on the data on this margin. So we can have same solution even if we get rid of those data on the outside of volume. So in that case, it is called sparse. It is sparse, and therefore it has some advantage over memory and scalability. So in other words, it can handle big data compared to some other kinds of machine learning algorithms. I think that those three are the main advantage of maximum margin classifier up to now. And it is even there will be some more strengths introduced right after this. So I want to talk about what if data are non-linearly non-separable? There are basically two remedies to this problem. One is slack variable, what is called slack variables, typically denoted by the Greek alphabet psi, and the other is using kernels. Let's first investigate slack variable case. Let's say the data configuration looks like this. This is clearly linearly non-separable, so there is, if we apply this kind of formulation to this configuration, there is no solution. There's no way of linearly separating those data. Well, however, let's just treat these examples are outliers. It is okay to ignore such examples and find other boundaries. For example, treat these as a margin boundary, then find this kind of boundary. Treat them as an outlier, some noise. This is the basic concept. In order to do that, we introduce slack variable, which is we introduce slack variable, which is determined as the distance from where it's supposed to be. Here, this is slack variable for this example. We introduce slack variables for each example, and distance from where it should be. The degree of violation. So the optimization criterion is while maximizing the margin, we want to minimize those kind of violations. So we want to make a compromise between the two criteria. So final optimization criteria look like this. to here because I wanna make two equations into one equation. yi is a class label which has value of +1 or -1. So this clearly states these two equations in one equation. And anyway, select variable go into here. All the examples should, for example, class circle or +1 has to value larger than +1. But it is okay for some example to have value less than 1. So we put those tolerance as another free variable. The free variable can have value larger than so non-negative value because because we want psi to be the extent of violation, and examples in this area has hasn't done any violation. So psi for these variables are 0, and but only non-zero for those who invade the boundary. However, in order to balance between the violation and maximizing criteria, we introduced another free variable, which is specified by user. 여기까지 좀 이해가 되시나요?
저기 서브젝트 다음에 나오는 식하고 만드죠.
네. 그러니까 yi가 각 트레이닝 이그젬플의 레이블인데 +1 아니면 -1의 값을 가지도록 해놨기 때문에 여기서 사실 두 줄로 쓴 거를 한 줄로 쓴 거예요. 왜냐면 +1일 때랑 -1일 때 -1이면서 도어가 바뀌니까 이거랑 똑같이 되거든요. 그래서 그 사이는 이제 리니어 클래시파이 못한 것들에 대해서 붙는 페널티인데 여기서부터 얼마나 떨어지는지를 나타내는 거고, 근데 당연히 이제 최대한 이런 게 없도록 하면 좋으니까 그걸 미니마이즈 하는 크라이테리언이 붙는데, 우리 원래 맥스마징 크라이테리언이랑 이거랑 두 개를 동시에 하다 보니까 둘 중에 가중치를 얼마나 줄지를 C라는 프리 베리어블이 붙게 됩니다. So this scheme introduces free variable which makes the problem less elegant but more practical. So this whole concept can be summarized as I think if you're familiar with neural networks, you are familiar with the concept of allowing training error. 더 붙여야 되나요? allowing training error. 그러니까 it is core concept in machine learning that the high training accuracy doesn't always yield test or generalization accuracy. So this can be viewed as some sort of regularization that, in some sense, allowing training error. So by this means, we can now separate the data which are not linearly separable. So and then I really want to introduce to you kernels. And how many of you are not familiar with positive definiteness? The metric, positive definite 매트릭스랑 별로 안 친하, 잘 모른다. positive definite. kernels, as support vector machine is one of the most important algorithms in machine learning. Kernels are also one of the most important concepts in machine learning. There was a really big boom in kernels around 2000 that actually coincided with the boom of support vector machine. Well, kernels have uses other than support vector machines. For example, Gaussian process, kernel density estimation, and what else? Clustering, things like that. So, kernels are very important concept. So you should, as a rookie, you should be very familiar with kernels. But before I introduce the definition of kernel, I would like to introduce some motivations. One of the motivation is what is called Kohl's theorem. As far as I know, this is just more like an intuition. It's not really a theorem, but it's just named as a theorem. So, data are This is the intuition that data are more likely to be linearly separable in a high-dimensional space. So if you project data into high-dimensional space, if I write that, if I project data which lives in R to the d-dimensional real vector space, to some higher dimension, d prime, and d prime larger than d, it is more likely to find a linearly separating hyperplane among the data. This is an intuition from Tom Hopper, which is a really one of the founders of machine learning, I think. Yeah, this is the basic motivation. Because in high dimension there is more space, more volumes, so it's more likely. Well, this is not, of course, not. I mean, it is not guaranteed. It is more likely, so it's not 100%. It is a very empirical statement, yet practically validated for many cases. Well, this is Kohl's theorem. So why don't we? So our SVM, our maximum value classifier, is not separating the data. So why don't we project our data into high-dimensional space, then finding a separating hyperplane there? So that's a pretty viable strategy, and that's what we are going to do right now. However, projecting high-dimensional space is not always a good idea, because there should, if dimension is really huge, these kind of computation should be very demanding in terms of both this computation. Well, yes, just projecting one data is viable, but what if there are thousands of data? What if we want to calculate some kind of product or some other operation on this data, this projected data? Then it would be, there should be a hard computational bottleneck. And well, these methods are built, these methods are invented approximately like 20 years ago. 20 years ago, the computers aren't that smart as now, so computation is computation really matters to them. Anyway, therefore they try to avoid this kind of computation while exploiting the benefits of high dimensionality. That is achieved by kernel trick. Let me first introduce the basic idea of kernel tree. Kernel tree, well, of course, not every operation on this. I will first define this. I will define this. I will call this space as a data space. I will call this space as a feature space. So we project, well, this term might be misleading, but let's just think it. I will project data in data space to feature space. We don't know what it will be, but it should be high dimensional. Well, the kernel tree is some operation, especially dot product or inner product of two points in feature space can be exactly calculated by some other function which is computationally less demanding. This is kernel tree. So by kernel tree, we are treating high dimensional space implicitly without saving all the d prime elements of vector of d prime elements. This is the basic idea of kernel tree. Any questions regarding this? I will try to introduce the definition of kernel. First of all, kernel is a function that takes two arguments in terms of what we say in programming language. It takes two arguments, basically two vectors in d-dimensional space, and outputs something scalar. That's the kernel function. But there's one more condition. Kernel function is this is really and this, and if we make matrix large K, some matrix large K is positive semi-definite, where K ij element is made up of this kernel value. N by N matrix for any I don't know if this works for you guys. Let me first explain it. 그러니까 커널이라는 거는 두 개의 벡터를 받아서 하나의 실수를 내는 그런 함수인데 거기에 어떤 특정한 성질이 있는데 또 뭐냐면 커널 값들로 만든 어떤 매트릭스가 항상 포지티브 세미 디피니트하게 하는 그런 함수가 커널이라는 거예요. So kernels, valid kernels, if a function to be a kernel, then it should satisfy this condition, which is a matrix large K, which consists of kernel values as a component, should always be positive, semi-definite. 잘 와닿지 않을 것 같으니까 예를 들면은 if we have three data, x1, x2, x3, then a valid kernel function we can make large K by from this arbitrary data. So first element should be x1, x1, k x1, x1, k x1, x2, things like that. And the second, this element should be x2, x1, da da da. So here, k x3, x3. This kind of matrix, we can build this kernel matrix from any kernel and any given data. And if that kernel is a valid kernel, real kernel, and this matrix should be positive semi-definite. This is the criteria or definition for kernel function. 혹시 질문 있으신가요? The key point is if you choose any data, any non-zero vector, any vector in the d-dimensional space, it should be positive semi-definite. That's a really tricky part. Not even just these three, but maybe 100, maybe 2, maybe some random numbers. It should always be positive semi-definite. So to emphasize such aspect, people sometimes call kernel as positive semi-definite kernels, but in field of machine learning, people assume the positive semi-definiteness of kernels, so people just say kernels. So let's be clear. Then what's positive semi-definiteness? And what is positive semi-definiteness? If a matrix A is positive semi-definite, we use this kind of symbol. The definition of positive semi-definite matrix is for all non-zero well, the definition of positive semi-definiteness is, well, somewhat similar to that one. Anyway, or any non-zero vector, the value A, x transpose A, x, should always be greater or equal to 0. This is the definition of positive semi-definiteness. Sometimes we need positive definiteness, not semi-definite. In that case, we get rid of this equality. I don't think you guys seen it before. You guys must have seen this before many times. Okay. Well, this is closely related to concept of ax squared is larger than 0, or in scalar world. This is positive semi-definite. And there are many positive definite metrics are very important, and it appears recurrently, like repeatedly in mathematics and machine learning. So you should be very familiar with positive definite matrices. And one other property of positive semi-definite is just for your reference. It's one other interesting and useful property is, if A is positive semi-definite, all eigenvalues of A are non-negative if it's positive semi-definite, and all eigenvalues are positive if it's positive definite. So these are important properties. And there are also negative definite and negative semi-definite, which can be obtained by just flipping all the inequalities in this page. Okay then. Then I want to introduce you the Mercer's theorem. This is really a theorem, not like Hilbert theorem. Mercer's theorem states that this is Mercer's theorem. So some two arguments function is a valid kernel. Then the theorem states that there exists some kind of one argument function phi, such that its inner product consists of kernel, that kernel function. So in other words, kernel function can always be decomposed into inner product of some other function. So for more clarity, xi, if I put xi as j, there is xi. So that's what we have talked about in the kernel tree section. So it just buys kernel tree. So if we use kernel, validated or proven some kind of kernel, it can be decomposed into such vectors. Safely. Yes. Well, the most famous kernel example is radial basis function kernel, which is radial basis function kernel or Gaussian kernel. They have many names. Well, there are many kinds of kernels. For example, Laplacian kernel, exponential kernel, polynomial kernel, rational quadratic kernel, and things like that. And you can even make your own kernel by checking the positive semi-definiteness of the kernel matrix. Anyway, well, among all of them, this kernel is the most famous and most popular one, and used for supervector machine very often. It has a sigma value as a free parameter. So using kernel function means that you have another free parameter. You should note that. And often choice of those parameters is very crucial in any kind of application you use in kernel. So when you get to use kernel parameter selection is very important issue. Anyway, so we have kernel tree, then 모든 걸 다 설명하기 위해서 사실 듀얼 폼을 라그랑지 멀티플라이어 가지고 푸는 걸 했었어야 되는데 이제 그걸 안 했으니까 제 정성적으로 설명을 할게요. So if we go to the dual form of this formulation, we will get a bunch of inner product of data points. I won't introduce the whole detail, but just have in mind that we have a bunch of inner products in its dual form. Dual Lagrangian dual function. We have a bunch of dual forms. And if we replace it with let's assume we can assume that all the data has projected into feature space, which can be exactly calculated with less effort by using kernel function. For example, using a radial basis function. Replacing all the inner products into kernel function is an extension of maximum margin classifier into high dimensional space, which can handle nonlinear. As you can see, the kernel functions are often very nonlinear. So if we replace this inner product with kernel function, supervector machine is running on the feature space, very high dimensional space, and that will, since the projection is nonlinear, the boundary found in the data space is nonlinear. This is really an amazing part of kernels and supervector machine. All the things coincide together to yield such a result. 제대로 보실 기회가 있으실 것 같고. Since we are running out of time, I wanna end this lecture with a few remarks. But not as impressive as those kernel trig or convex optimization formulation. My last two topics are practically important because one is multi-class problem, multi-class generalization, and the other is my practical advice on running a real SVM. Let me do it quickly. So as I said, binary linear classifiers and therefore supervector machine are innately binary classifier. So you cannot handle more than two classes. To relax such limitation, there are two approaches I've proposed. One is so-called one versus one approach, and the other is one versus the rest approach. So if you have successfully built binary linear classifier, you can apply it many times. So there are three classes. In this case, if I use the first approach, I train three classifiers, which the first classifier separates. First classifier separates tells if it's 0 or x. The second classifier tells if it's circle or triangle. The third classifier classifies x or if the trained test example is x or triangle. So in this case, if we have k classes, we have to train all pairs, which means k combination 2, which yields k minus 1 or 2. Okay. Well, the second approach is one versus rest. It classifies class circle versus the rest. And the other classifier classifies x versus the rest. The other one, of course, classifier versus triangle versus the rest. So in this case, we have to train only k classifiers. As we have multiple classifiers, we get to do majority board. So what is called majority? So let's just make a quick example. We have three classifiers, classifier 1, 2, 3, and classifier 1, 2, 3 get to answer. So one answers that this example is circle class, not x class. The second classifier tells it's circle class, and the third classifier tells it's triangle discussion in the book PRNL written by Chris Bishop. These two, although let's first say this. So the first one scales badly. If k is large, this needs k square of classifiers. This scales really badly, so it cannot be applicable to problem, for example, problem which has 1,000 class to be classified. However, this scales linearly, so it's much more applicable. Well, as you might expect, there are inevitable, ambiguous reasons here. So, indeterminable. For example, what if the class 2 and 3 outputs, class 2 outputs, triangle, class 3 outputs, x. Then what should the prediction be? It can be determined. Well, this has smaller undeterminable region, but both of them cannot avoid this problem. They should be, in this case, one example can be, one remedy can be just red. If everybody disagrees, then you can just coin toss, or you can try to measure it based on some distance between the hyperplane, but still, there is no principled way to handle such ambiguity. This is a multi-class problem. This is how to deal a multi-class problem with support vector machine or other all linear classifiers, not even support vector machine. You can apply it to Fisher discriminant analysis or logistic regression or other kind of linear classifiers. This is the if you're interested in this problem, you should look up Pattern Recognition and Machine Learning by Bishop. I think it's chapter 3. It has really good discussion. Well, my last words will be in 5 minutes. I have 3 advices from practical application of support vector machine. This is from not totally from me. It's from one of the most famous implementation of support vector machine is libsvm. It is maintained by Taiwanese researchers. I think his name is Lin or something. And in their web page, there are a bunch of good materials other than their code. And there is also an article explaining the practical advices on SVM. I'm summarizing their results. The first one is use RBF kernel if you don't know anything. Because radial basis function kernel, in theory, it projects the data into infinite dimensional space. So this is one of the strongest kernel in machine learning, even though it's very simple. And the computation bottleneck is not very, let me write down. So infinite dimensional, the computation bottleneck is just moderate. It's not very fast, but moderate. And only one hyperparameter. As you see, there was a sigma kernel parameter. But some other kernels have multiple kernel parameters, which means harder performance tuning. So if you don't know anything, you should use RBF. It's their recommendation. The second advice is you should do hyperparameter optimization. This is usually done by what is called grid search cross-validation. It's usually done by cross-validation and grid search. How many of you don't know cross-validation? No. Okay, good. Grid search means that, so for example, if you use RBF with SVM, you can basically have two free parameters. One is C, which comes from select variable, and the other is sigma, which comes from RBF kernel. So the values of these two hyperparameters are really crucial to the performance. You have to tune it at least close to the best one. So in order to do that, you do grid search. So you make a table. On the columns, different values of C. On the row, on the columns, different values of sigma. You do cross-validation test for every combination, and you pick the best one. This is necessary, but it takes a lot of time, of course. Well, their recommended strategy is two-pass grid search. So you first define a coarse grid. So then 처음에는 엄청 이 그리드를 넓게 잡아가지고 막 이제 0.1, 막 100, 만 이렇게 넓게 잡아가지고 대략 making a coarse grid means you have it let you have a rough feeling of approximately what region is performing very well. So then you get more finer grid in this area to get best results. So I found that many people don't even care about these parameters and reporting. Many don't care about this result. So this is really crucial. And the third one. This is my last comment from this lecture. If data dimension of the data is high enough, just use. So in other words, to make more stronger emphasis. So the last one is, if the data's dimension is high enough, for example, it's very common in the bioinformatics setting. For example, gene microarray data, number of human gene is approximately 22,000. So it means that it's 22,000 dimensional data. So it's already high enough. And their dimension is like 22,000, and the number of data is typically like around 100. So it means the data is already in pretty high dimension, so you don't need high dimension projection. It only using kernel in this case only causes computational complexity and free parameters. So if you don't use kernel, so in this people sometimes call linear SVM. Just naive maximum module classifier. If you use linear SVM, you have several advantages. Advantages such as like less computation and less parameter, things like that, and still decent performance. Actually, 한마디를 더 하자면은, there are separate implementation of linear SVM. So I mean, in live SVM package, there is a, I would say, let's say there are two different implementations. Just ordinary SVM with kernels and SVM without kernels. Why this is in a separate implementation? Because it optimizes even further than, in terms of program implementation. 그러니까는 커널, 그러니까 리니어 SVM 만약에 써야 되는 상황에서는 리니어 SVM이라고 따로 구현된 거를 쓰셔야 되는 게 그 커널을 안 쓰는 걸 가정하고 코드를 더 옵티마이즈를 해놔가지고 훨씬 빠르게 돌거든요. It's much faster than ordinary simple vector machine assuming usage of kernel. So if you get to use linear SVM, you should use separate implementation. This is what I prepared for today. I'm quite sorry that I couldn't go over the Lagrange multiplier part, but this should be more practical. So any questions so far?